What if the Earth just stopped spinning? Like a complete sudden stop right now. Would we all just go flying?
Not slowed down, not over years, stopped in an instant, right now, while you're standing on it. Let's set the rules first. This is a sudden stop, not a gradual one. The planet keeps orbiting the sun. Only the spin halts. No warning, no mercy. Sounds simple, right? It is anything but, because everything you've ever trusted about this planet, gravity, weather, the ground beneath your feet, depends on that spin more than you realize. You've never questioned it. Nobody has, really. It's the one constant every civilization in human history has been able to count on, from the first person who noticed the sunrise to the last satellite launched this year. And the moment it stops, the world you know ends in about 90 seconds. Here's what the science actually says would happen. Right now, if you're standing near the equator, you are moving, not walking, not driving. You are being carried through space at roughly 1,670 kilometers per hour, just over 1,000 miles an hour, faster than a commercial jet. You don't feel it, because everything around you, the air, the ocean, your coffee cup, is moving at exactly the same speed. That's the trick. Motion you share with everything else feels like stillness. But physics doesn't forget momentum just because the planet asks nicely. If the ground beneath you suddenly stops, you don't stop with it. You keep going, at jet speed, in whatever direction you were already facing. This is the first stage of the scenario, and it's the most violent one. The instant the crust stops, everything not bolted directly into bedrock keeps moving at that original speed. Buildings shear off their foundations. Trees rip out of the ground. Oceans, still carrying their own momentum, slam forward like a bathtub yanked out from under the water. Entire coastlines would be scoured by walls of water surging toward the equator at hurricane speed. Except this isn't wind-driven, it's the ocean itself refusing to stop. Meteorologists studying storm dynamics already know how devastating 300 kilometers per hour of moving water can be. Now multiply that by 5. And the air? The air keeps moving too. Earth's atmosphere doesn't just sit on top of us, it spins with us, all 5.5 quadrillion tons of it. If the ground stops but the atmosphere doesn't, you get wind. Not storm-level wind, not hurricane-level wind. Wind close to the same speed the ground just lost, howling across every surface of the planet at over 1,000 kilometers an hour. That's faster than the strongest tornado ever recorded. It wouldn't be isolated to one region, it would be everywhere all at once, scraping across continents like sandpaper. Think about what that actually means for a moment. Forests wouldn't just lose branches, they'd be flattened, root systems torn straight out of the soil in a single gust. Sand and loose soil would be lifted off the ground entirely, turning the sky into a haze thick enough to block sunlight across whole continents. Structures engineered to survive the fiercest hurricanes on record, built for winds topping out around 300 kilometers per hour, would face forces more than 3 times stronger, sustained for hours, not minutes. Nothing in modern engineering was ever designed for a planet-wide event like this, because until now, nobody had a reason to design for it. So within the first 2 minutes, before anyone has time to process what's happening, the surface of the Earth has already been reshaped by wind and water alone. But that's only the beginning. Because losing spin doesn't just cost us motion, it costs us shape. Here's something most people don't think about. Earth isn't a perfect sphere. It bulges at the equator by about 21 kilometers compared to its polar diameter. Isaac Newton worked this out centuries ago, using nothing but math and an understanding of rotational force. The planet bulges because it spins. Centrifugal effect pushing mass outward at the equator, the same reason a spinning pizza dough stretches wide in the middle. Stop the spin, and that bulge has no reason to exist anymore. Gravity would slowly pull that equatorial mass back inward, redistributing the planet's shape toward a perfect sphere over thousands of years. Slow compared to the wind, but permanent. The coastlines we know, the geography we've mapped for centuries, would eventually be redrawn from the inside out. Would the destruction stop there? Not even close, because Earth's rotation isn't just moving rock and water and air, it's generating something invisible that protects every living thing on the surface, our magnetic field. Deep inside the planet, molten iron churns in the outer core, and that churning, combined with Earth's spin, creates what's called the geodynamo. In 1995, geophysicist Gary Glatzmeyer, working with mathematician Paul Roberts, built one of the first supercomputer simulations to successfully model this process, showing how the moving, spinning core generates the planet's magnetic field and even predicting its occasional pole reversals. Their work confirmed what scientists had suspected. Rotation isn't a side effect of the magnetic field. It's a core ingredient in creating it. Stop the spin, and that dynamo doesn't fail instantly, but it begins to weaken and destabilize almost immediately, since the rotational forcing that organizes it is gone. And the magnetic field isn't decoration. It's a shield. It deflects the solar wind, the constant stream of charged particles blasting off the sun, and it's the reason we still have an atmosphere at all, instead of one that got slowly stripped away like Mars's did billions of years ago. Weaken that shield, and the Van Allen belts that trap dangerous radiation start to falter. Satellites fail, communication systems break down, and over time, surface radiation levels climb to dangerous territory, especially at higher latitudes, where the shield was already thinnest. Now here's the twist that makes this whole scenario even stranger. Earth would still be orbiting the sun normally. It just wouldn't be spinning on its axis anymore. That means one full day, sunrise to sunrise again, wouldn't take 24 hours. It would take an entire year, because the only reason we get day and night every 24 hours is that we're spinning independently of our orbit. Take that away, and one side of the planet faces the sun for 6 straight months, while the other freezes in 6 months of total darkness. Picture it. Half a year of unbroken daylight, temperatures climbing past what most life can survive, while the far side plunges into a frozen night colder than Antarctica's harshest winter. It's not unlike what already happens to Mercury, a planet so slow spinning relative to its orbit that its day-night cycle stretches across most of its year, leaving one face scorched and the other frozen for extended stretches. So what actually happens to life on Earth in this scenario? It doesn't go extinct instantly, but the habitable zone collapses fast. The narrow ring between the blazing daylight side and the frozen night side, something like a permanent, planet-wide twilight strip, becomes the only place with survivable temperature swings. Everywhere else becomes either an oven or a freezer, depending on which half of the year-long day you're standing in. Agriculture, as we know it, stops working within a single cycle. Ecosystems evolved around 24-hour rhythms, from a plant's photosynthesis schedule to a predator's hunting pattern, would be thrown into chaos that most species simply couldn't adapt to in time. Here's the part that should actually make you feel better, though. This isn't something that could realistically happen. Angular momentum is one of the most stubbornly conserved properties in all of physics. Nothing in our solar system has anywhere near the force required to stop a planet's rotation abruptly. Not an asteroid impact, not a passing comet, nothing we've ever observed. Earth's spin is slowing technically, but by about 1.7 milliseconds per century, caused mostly by tidal drag from the moon. At that rate, we're not looking at a stopped Earth. We're looking at a very, very long, very gradual process spanning billions of years, one our descendants many generations removed would barely notice happening around them. But that's exactly what makes this thought experiment so revealing. We don't think about spin. We don't feel it, we don't see it. And most of us go entire lives without considering that the ground under our feet is a high-speed vehicle we've been riding since birth. Your sense of still is actually motion, shared and synchronized with an entire planet moving in perfect unison. The sunrise you barely glance at every morning is proof the machine is still running exactly as it should. Consider how much of modern life is quietly built on top of that same spin. GPS satellites calculate your location by measuring signals against Earth's precise, predictable rotation. Global time zones exist only because different parts of the planet face the sun at different, ever-changing moments. Even your body runs on it. Your circadian rhythm, the internal clock regulating sleep and hunger and alertness, evolved around a 24-hour cycle because that cycle has never once wavered in the history of complex life on this planet. Every alarm clock, every flight schedule, every sunrise photo on your phone is, in a very real sense, a small tribute to a spinning rock nobody asked permission to depend on. Stability, it turns out, isn't the absence of motion. It's motion so consistent, so reliable, that it disappears into the background of everyday life. So back to the question we started with. What if the Earth suddenly stopped spinning? The honest answer isn't really about wind speeds or magnetic fields or year-long days, even though all of that is real. The honest answer is that you're already living inside the answer to a very different question. What does it take to build a world this stable? It takes a planet spinning fast enough to stay whole, slow enough to stay livable, and steady enough that you never have to think about it at all, until someone asks you to imagine what happens the moment it stops.